Hi guys, today I would like to discuss Fermat's theorem again. Uh, this is Fermat theorem, and Fermat theorem states as follows: if p, variable p, is a prime and a is a positive integer, now there is a condition here for this positive integer is not divisible. So a is not does not divide the prime number p, is not divisible by p. Now this is the condition here. If that's if this occurs, then we have this relationship in modular operation. We can state that the positive integer a raised to the power prime minus 1, the prime number minus 1, is equivalent or congruent with 1 with respect to mod or modular p, which is p is the prime. So this is the rule. This is Fermat's rule. This is the primary rule. And of course there is a variation of this rule, which is, of course, if we let's say that we multiply both sides by a, multiply both sides by a, then we have this new relationship. So then a, so you have a times a to the power p minus 1, so we have a to the power 1 plus a to the power p minus 1, so we'll end up having a to the power p is congruent with a mod p. So this is a variation of Fermat's theorem. Now, to give you an example, of course, so we pick two numbers, one for p and one for a. For the sake of argument, let's say that p is prime number, which is, let's say, 11 is a prime, and of course 11 is only divisible by itself or 1, so p is given. Now we need to look for a such that it doesn't divide p, and in this case it could be we can choose 3. A is equal to 3. So as you can see, 3 doesn't divide p. So then in this case, if we look at the relationship here, so we have a, which is, so you can use 1 first. This is the original one, and this is 2. So we can state that for a is 3 raised, if you want to use 1, so it will be 3 to the power 11 minus 1, which is 10, is congruent to 1 mod 11. Okay, so of course, this is very useful for simplification of when computing modular or performing modular arithmetic. So this is the result, and also, of course, if you apply 2, it will be 3 to the power 11, which is the prime, congruent to 3 mod 11. course here is the variation. It's obvious we have the prime and the exponent are the same, so that's the variation. Okay, so let's take now a different example. So example 2. So example 2, assume that we want to perform this computation or evaluate 3 to the power, and let's choose a large one, 3 to the power 201. We want to find out this one in mod 11. So we're using the same prime number. Okay, now notice, okay, the condition for Fermat's applies. So using Fermat's theorem, it states that A in this case, of course, is equal to 3 and P is 11, and the condition is met, so the P is prime and A doesn't divides P, so we can say that A, which is in this case, if we apply it, will be A to the power P minus 1 congruent to 1 mod P. So again, so here 3 to the power 10 is equal to 1 mod 11. So this is true. This is from the theorem, but look, if you look at our problem is different. The problem is this. Problem is that we have 3 to the power 201, and here we have 3 to the power 10. So how we can make use of Fermat's theorem? So again, let's take a look at the original problem, which is we need to compute 3 to the power 201. Now it's, of course, everything now here is mod or module 11. So let's, using the exponentiation theorem, so we can say that 3, we can express it as 3 to the, so we want to express it very close to this one, so we want to express it as 10, so to the power 10. Now if we raise the whole thing to power 20, so that's 200, and then we multiply by 3 to the power 1, of course, so this will be equivalent. Okay, in terms of exponentiation, this is 201, this is 10 times 2, that's 201. Okay, and of course here everything is mod 11, and let's see how we can simplify this. So so when you have 3 to the power 10, so basically you can do it that so we can say that here, so we have we already have 3. All right, that's 3. Now let's find out what is this. So 3 to the power 10, if you have 3 to the power 10, okay, if you substitute this one, 3 to the power 10 is equal to 1 mod 11, so basically this is equal to 1 to the power 20, and of course this is mod 11, and the result, of course, is going to be equal to 3 mod 11. So 3 to the power 201 is equal to 3 mod 11. Okay, So in this case, we were able to perform this problem using Fermat's rule. Okay. Let's take a look at another example, just to make sure that this is going to be clear. Now assume that you have, this is example 3. Let's say that you have 7 to the power of 36, and you want to perform this in find 7 to the power 36 mod 19. Okay, so in order to solve this one, so let's take a look at Fermat. Let's try to make use of Fermat's rule. So again, to answer, I'm going to change the color to red, just to, this is the answer to this problem. So we express 7 to the power 36, we express it as 7 to the power 18, okay, and of course here to the power 2. So 18 times 2, that's 36, and of course we want to perform it using mod 19. So we just expressed the exponentiation and the number in different format. Now then we can try to capitalize on Fermat theorem. So the Fermat theorem says that, okay, here Fermat theorem says that 7 and 19, they are, 7 doesn't divide 19, 19 is a prime number, so 7 to the power 18 is equal to 1 mod 19. Okay, so 19 is a prime number, so this is p minus 1, this is Fermat's theorem. So in this case, we can say that it is this will be 1 according to the Fermat theorem. 1 to the 1 square will be 1, so the answer to this one is going to be equal to 1 mod 19. Okay, so that's the answer to this one. Now of course, we can verify it. Okay, I'm just going to show you with a calculator. Okay, just minimize this one. Okay, so I don't know if the calculator is gonna show. All right, but in this case I have 7 to the power 36, raise it to the power 36, that's 7 to the, give us a huge number, obviously. Of course, that's why if you want to find the mod of to 19, so the answer is 1. This confirms my result. So actually you can confirm it with the calculator. All right. So this is briefly Fermat's theorem, and I will in the next video I'm gonna show you the Euler's theorem and Euler's totient function. Thanks guys. This is Professor Darwish, and I'll come back to you shortly.